Okay, so number 57, a rubber ball bounces. We'd like to understand how the ball bounces. So A rubber ball has been dropped and is bouncing off the floor. Draw a motion diagram of the ball during the brief time interval that it is in contact with the floor. Show 4 or 5 frames as the ball compresses, then another 4 or 5 as it expands. What is the direction of acceleration vector during each of these parts of the motion? B, draw a picture of the ball in contact with the floor and identify all forces acting on the ball. C, draw a free body diagram of the ball during its contact with the ground. Is there a net force acting on the ball? If so, in which direction? And D, write a paragraph in which you describe what you learned from parts A to C and in which you can answer the question, how does a ball bounce? So this question is quite long, so we're just going to try to go through this as best we can. So the motion diagram. A good way to try to visualize this situation is just to write it out, draw it out what this actually looks like when you're looking at a ball bouncing. So we have this ball compressing. For this first half, we have a turning point where it's not really doing necessarily anything, and then we have an expansion, and we have the first contact and the last contact. So our motion diagram looks something like this, with the compression section having these velocity vectors decreasing in length as it compresses, and then the turning point just being a simple dotted line. There's nothing really happening during the turning point, so there's really nothing to put here besides just something to signify that we're continuing through a motion. And then during the expansion, these velocity vectors are getting bigger and bigger and bigger. So how do we find the direction of this acceleration vector? Well, I found this trick online actually, so it's kind of weird, it's kind of unconventional, so try to stick with me here. So let's take two vectors, v0 and v1. So we can see that v0 and v1 are different lengths. v0 is bigger than v1. And so if we can pretend that I can do whatever I want to these vectors. So let's pretend that this part, this dot of this vector is completely fixed. I can't move that. But I can move where this arrow is. Pretend I can push it up, or I can pull it to make the vector longer or shorter, or I can change the direction however I want. Now to determine where the acceleration direction is, all I have to do is ask myself, what do I have to do to v0 to look like v1? Well, I just have to push it up, and that upwards motion is actually equal to the change in v. It's upwards, and so the direction of acceleration is going to be upwards as well. And you can do this for v9 and v8 and do the same thing, and you'll find that you have to pull or push something upwards again as well, and then that upwardsness is going to continue through the turning point. So we find that the direction for this acceleration vector is up all throughout the entire movement. Now for B, we're just drawing a quick little diagram of what this looks like, of what the forces are acting upon this ball. So we have our ball, and we can see that the force of gravity is acting on the ball as well as the normal force going in the opposite direction. Now for C, a free body diagram of this question, we have the normal force and we have the force of gravity. And because we know that the ball does eventually bounce, then we know that the normal force has to exceed the force of gravity at some point. So because of this discrepancy between these two values, there has to be a net force that is traveling in the direction of the greater normal force, which is upwards. Now for D, the big picture of what we learned. So we learned that while a ball compresses and expands and goes through a turning point while it bounces, the entire time the acceleration direction is upwards. And because of this, we know that the ball has to bounce if this acceleration is upwards the entire time. We also learned that the forces in question were the force of gravity and the normal force, and we found that there was a discrepancy between these two forces, to which the normal force was greater than the force of gravity, which again just reinforces the notion that this ball has to bounce. And so our learning objectives today were to determine the direction of an acceleration vector, to draw motion and free body diagrams, and to interpret those diagrams as we have been this week and partially a little bit of last week with the motion diagrams. Thank you very much. I hope you have a lovely day.